So hello everyone, welcome to our webinar series. Today we want to talk about Electrospun membranes for photocatalytic applications. We will present here these membranes based on polyacrylonitrile membranes containing photocatalytic nanoparticles. These hybrid membranes will be tested in different photocatalytic membrane reactors towards the degradation of pollutants. Today's speaker is Dr. Mathieu Grandcolas, research scientist focused on nanomaterials development and functional materials from Sintef, which is the largest independent contract research organization in Scandinavia and the fourth biggest in Europe. First of all, we want to talk quickly about Elmarco, and I want to give a word to my colleague Katarzyna.
Yeah. So hello everybody. It's my great pleasure again to talk about a little bit about Elmarco. So who we are. Elmarco is a global company. We are delivering technologies to many countries. Basically, we are focused, our core business is dedicated to supplying industrial scale machinery for making nanofibers. We are in the market for more than 20 years already, having a great experience in this technology. Briefly on how this technology look like. So basically, we have two electrodes where on the spinning electrodes we are depositing the polymeric solution by the moving carriage, as you can see on the short video, and the fibers are generated towards the collector, which is again the wire, but we are coating moving substrate, which can be any kind of non-woven textile or paper or any other flexible, let's say, material, which is rebind through the spinning chamber. And by that, we can manage to provide, let's say, two-dimensional coating of the substrate or surface coating of this substrate. What we're doing, as I mentioned, we're selling machines. So this is our complete portfolio of machines that we are bringing to the market, starting with a lab scale technology, lab scale machine. We call it NS Lab, and it's going through the pilot or semi-production tool, 0.5 meter size in the width, and ending up with the largest, let's say, equipment that we are producing, which is 1.6 meter industrial line, which is fully equipped machine, not only with let's say, nanospider sector, the section that's making nanofibers, but also other peripherals, which are forming altogether the entire technology, which is completely delivered to our clients. As mentioned last time, nanofibers can be used in many segments. This is just a few of them, which are the most developed. And today we're going to cover two segments, which is air filtration and liquid filtrations. Both are related to the research of our speaker today, and both are related to electrospun membranes for photocatalytic application. Now, eventually, I want to give a word to Mathieu. So please, if you can start sharing your screen, and stage is yours.
Thank you, Katerina. While I'm sharing the screen, I would like to thank, of course, Elmarco for the invitation, especially Carolina. I think she did a really good job for organizing this webinar. So thank you a lot for all the people in Elmarco. Just tell me if you see my screen and if you can hear me. Yes? Okay. So I would like to start by mentioning that we are not really purely speaking experts in electrospinning. We are mainly using electrospinning as a tool for a lot of different applications we have here in Sintef. So I think this is really a good forum and a good place to discuss the electrospinning for this very specific application that we have today. Electrospinning and photocatalysis is maybe not really common in the electrospinning world, so I was quite excited today to have this little presentation about this topic. I checked this morning actually, but if you type electrospinning and photocatalysis on Web of Science, which is one of the big platforms for scientists to check for literature, there is about 1,100 hits. So it's not really one of the main applications of electrospinning today, but it's certainly a really big scientific interest. So this is the outline of my presentation. I just would like to come back very quickly on Sintef, the presentation of our institute. It's a bit special how we are working here. I will, of course, try to present for photocatalysis and why we're using membranes, why photocatalytic membranes are interesting. And I will try to show you how we are making a membrane. And I think, again, this could be really good opportunity for a discussion for that, or future discussion together. And I will go through the different membranes. I have them with me also. I brought a few ones so we can discuss things. I will try to show you as clearly as possible what we are doing. So I think Ivan already introduced Sintef, but we are an independent, non-for-profit research. I have my window here in the middle. Research institute, which means we are not really working as basic research and education like university. We are not really a business, and we are a bit in between. We are kind of a multidisciplinary applied contract research. By the time I had this slide, I think we were the largest independent research organization in Scandinavia, but I think we just lost our place a few months ago. But we're on the top there. We are about 2,000 employees. And I think what is really our force also in Sintef, and we are working within 75 nationalities here, so which represent, I think, 25% of all the personnel in Sintef. So that's, I think, really a good force for us. The other type of institute, independent, non-to-profit in Europe, it's, I think I've found Fraunhofer, Vito, TNO, VTT, for example, just to give you an idea of other institutes. This is just a fancy picture I found for the different application we are working in. If you look on the left of the picture, you know, Norway has about, I think, 25,000 kilometers of coast. So we are working a lot with sea, subsea application, marine applications. But there is a lot of different other applications we are working in. And I think most of these applications could have application within electrospinning things. So it's really, for us, electrospinning has been a big interest also. Just quickly, our group, what are we working, especially here in my group, we're working with? We are mainly working with thin films and membrane technologies. And we have different prioritized research area. It's a lot on, yes, it's a lot on CCU. Of course, this is a big application for us. So we are working a lot with membranes. We have a project on CO2 conversion and photocatalysis. I will show you at the end of the presentation, but we are working with piezoelectric materials, additive manufacturing a lot, fuel cell, PEM fuel cells, mid-temperature, high temperatures, and a lot of with batteries also, which is, I think, quite a hot topic with electrospinning nowadays. Well, yeah, let's dig directly into photocatalysis. And I found this wording a few years ago, and I think it's very interesting. The solar energy which is hitting the Earth's surface is about 10 to 24 joules per year. I don't even know how many zillions this makes, but somebody clever made this conversion, and it's approximately 10,000 times the worldwide yearly consumption of energy. So one can really easily understand that if we put a lot of effort and if we can find some efficient conversion of all of that, it's really one of the most important challenge in the research and technology development. The first thing, of course, that most of people think it's solar panel, photovoltaics. But photocatalysis is really growing a lot, and we also have solar heating and a lot of different things like that. What is a photocatalyst? For this presentation, I tried to find a lot of different definition, and I found this one. I think it's a very simple and understandable one. A photocatalyst, it's a substance that is going to use light as the energy, and it's going to facilitate a chemical reaction. And there is a parallel to this. It's, for example, the chlorophyll in the plants. It's a typical natural photocatalyst. The chlorophyll is going to capture the sunlight, and it's going to turn water and carbon dioxide into oxygen and glucose. And here in the development of our material, we're using more or less the same principle. In the presence of light and water, this photocatalyst is going to create strong oxidation agents and electronic holes. And it's going to be used to break down the organics, for example, or to convert carbon dioxide. There is other application like hydrogen generation also. So this is a bit the basic definition of it. I will come back a bit more in details in another slide. But I think historically it's quite kind of interesting to see how photocatalysis emerged. One of the most famous photocatalysts is titanium dioxide. And this has been used in painting, for example, for decades. It's a natural pigment. You see, it's a white powder. It's a very strong white powder. And in the 20s, there was industrial revolution for the preparation of this powder. And lot of paints undergo chalking, so it's getting a bit brittle. The painting is breaking on the surface, and this was mainly because of a size effect. Natural pigment has quite large particles, at least above 0.5 micron in most of the case. So the photocatalytic effect is quite small. But when the particle size is much smaller, the photocatalytic effect was quite strong. So this has been described in the 1920s, in famous publication. But it didn't go. They didn't really exploit this before the 70s and 80s. There is this famous Fukushima and Honda effect for the splitting of water using photocatalysis. And since then, it has been exponentially growing. There's a lot of different applications for photocatalysis. We look a bit more in details. Photocatalysis, it makes use of a semiconductor. I tried to find kind of a figurative GIF recently, and I found this one. I think it's quite interesting to see that there is 3 fundamental states of matter when it comes to electrical conductivity. You have metal, for example, what is inside this string. There is copper inside, and this is a very good conductor. You have non-metal, glass, for example, or the plastic, which is around the wire. But there is a little fringe of material, which is called a semiconductor. And the semiconductor is characteristic by its band gap. So it's an energetic band which can be controlled, for example, and it has a lot of different applications. Like I said, titanium oxide is still nowadays one of the most common photocatalysts. It's actually the only commercial photocatalyst you can find on the market right now. The dream job for photocatalyst would be to use sunlight as the only radiation to make all this transformation. TiO2 is a bit problematic because it absorbs only UV light. So it needs a bit of modification, and I'll discuss this also a bit at the end of the presentation. I'm sipping coffee because it's still -11 in Oslo here, so it's still a bit cold. I need to warm up a bit. So if you imagine a particle like this, which is a photocatalytic particles, what it needs a certain amount of energy to fulfill this band gap. So what's going to happen, you're going to create some charges mainly inside the particle. So we have this electron moving and holes moving. And then you're going to have separation of these charges. And a lot of these charges are going to recombine. So basically, the electron you're going to excite on this particle is going to come back to its original state. And that's okay. And that's a phenomenon which is happening a lot in the photocatalytic nanoparticles. But if you can really separate these charges, and if they can reach the surface, you can use them for extremely powerful reactions. You have reduction. For example, oxygen is going to create superoxide anions or radicals or other type of radicals. What is interesting here also is that the organics themselves are going to be oxidized, or you're going to create these hydroxyl radicals. And I think hydroxyl radicals are the most, or in the top 3 of the most powerful radicals you can find in nature. For example, it's much more, or it's more powerful than ozone or chlorine or a lot of different radicals you can find in nature. So the nanometric size of the particle is very important. If you have to remember one thing about this slide, is this. And the second one is that we are creating extremely powerful reaction on the surface of the particles. You can find, of course, a lot of different indoor and outdoor applications. The most famous one is this one's the disinfection. It's a picture which I'm mainly taking in Japan. It's in Japan, it has been much more developed probably, I think, than in Europe. But they are coating, for example, hospital tiles to create a disinfection. It was really popping during the SARS viruses in 2002 or 3, something like that. There has been a lot of air purification systems developed, either for rooms, but also for industrial air cleaning. I think this is a French project within 10 years ago, I think. There is a lot of outdoor application. This one is quite impressive, actually. You have a layer of a photocatalyst on glass, and it's self-cleaning. It's cleaning the soot which is on the surface of the glass. Ital Cementi, for example, they developed photocatalytic cement. There is this famous church. I forgot which country it is, but it's working quite well, actually, and it's developed for a lot of different buildings. There is also an experiment in Japan for pavements, for photocatalytic pavements, for example. There is some study about mold development. You can paint your wall with this specific paint, and you will hinder the development and the growth of mold. Superhydrophilicity is another application of photocatalysis. I remember the first time I went to Japan, in the bathroom, you have the window, and there was no fogging on the surface of it. It's quite impressive. It's working quite well, actually. I think can somebody mute because I have an echo. Yes, anyway. Okay, but why would we use membrane in photocatalytic process? Because on the left here, see, you have if somebody can really mute their microphone, I barely hear myself. In slurry reactor, it's working very well. The photocatalytic wise, there is a lot of advantages of a slurry reactor. You have a fairly uniform catalyst distribution in the suspension. You have quite limited mass transfer. which is the fact that the pollutants and the photocatalytic particles are very close one to the other. But one of the biggest disadvantage of this process is that it requires a post-process filtration, and that's usually a very expensive process. So when you immobilize the photocatalytic particles in a reactor, you can have a continuous degradation, which is a huge advantage in this situation. Oh, thank you. There is no more echo now. Thank you. We have a laboratory size electrospinner from Elmarco. We're using this model, NS Lab model. And for us, it has been a bit of a game changer because we have a spinning electrode width, which is about 40 centimeter, 35, 40 centimeter with some border effects. And for us, it is extremely useful because maybe with 10, 20 milliliter of a solution, we can make about 20, 30, 40 membranes. Because at the laboratory scale, we are using, like, let's say 5x5 membranes, which is quite small. So that was very useful. That's a typical example. We have like a A4 electrospinning surface. So in this, we are cutting maybe 20 membranes to use after. So it's very useful. We are not using it roll to roll because there is a roll here on the upper left corner, which is going in between the two electrodes. So technically you can produce meters of photocatalytic electrospun membranes. We are using it static, but I suppose this could be easily upscaled, which is another advantage of this method. So for the development of membranes, we have started from polymer, and we tried to move toward oxides, but we quickly came back to a polymer situation. I'm going to try to explain this. When we first worked with electrospinning, we used a lot of time to prepare different electrospun membranes. When you have to work with the amount of polymer you have in the solution, of course, the different polymers, and this is also something extremely important. And then we would perform a coating, for example. And I was okay for most of the cases, but the photocatalytic conversion was not excellent at this time. So what we try to do is to make pure oxide nanofibers. And that's also quite easy. You can use, for example, PVP or PAN or whatever, and you put a titanium precursor inside, you electrospun and you calcine it, and you have an oxide. But it's extremely problematic because, for us, because there is a big shrinkage. I remember putting a piece the size of my fist into the oven, and you calcine it, and you come back, and it's like extremely small. So there's a huge shrinkage for that. And it's also very fragile. You can, for example, you can take a piece of this electrospun membrane like that, and you can put it in between two sheets of glass or ceramic, and you can make a really nice flat membrane. But the second you're going to try to manipulate it, it's very fragile. So we had a lot of problems for this application. So we basically came back to polymer-based nanofibers with nanoparticle inside or at the surface of the nanofibers. And this is what I'm going to try to develop more now. Why polyacrylonitrile? It's really high tensile strength. It's very flexible in nature. It has a good chemical stability. We are mainly working for water-based applications, so it's not really a problem. But and for the thermal stability, it's a bit the same. We're not really working at high temperatures, so it's not a big problem. But it's nice to have a material which is sustaining these problems. For me, the most important is that it's soluble in DMF. DMF, it's rather a highly toxic solvent, but it's extremely good to disperse most of our precursor. It has a high boiling point, so you can even apply some heat to the solution you want to use. It's very useful. I think we have to go away from DMF in the future. But really, that's a question for you and us maybe to discuss one day. What other material can we use? We are quite happy with PAN, but if there is any other materials, I really would like to hear from it. It would be very interesting to talk about that. So this is the way we are making the membrane, and this is very important to take it in this order. When we have students arriving in Sintef, we always spend quite a lot of time to develop that. First, what we do is we disperse the nanoparticle in DMF with quite a long time. We use at least 1 or 2 days to really disperse them well. We use ultrasound. And you can see that in the particle size distribution is quite narrow. So we can have quite a narrow particle size distribution. The particles are well dispersed. When you're using that small nanoparticles, you will never have one particle next to the other one. You will always have this kind of agglomerate. But for us, it's quite fine actually. Then we add the PAN very slowly at this kind of molecular weight. It's like long spaghetti. If you don't do it that way, it's very difficult to take it back. And we electrospin at 60 kilovolts. And we have this kind of very nice image. We use 10 to 60% of titanium oxide, so it's quite a lot. But I think this image will show the gradual loading of titanium oxide you have in and on the fibers. At 10%, it's not that much actually, and we still have quite a lot of agglomerates between 10 and 30%. But I have the feeling when I see this picture that it's getting more and more homogeneous. Homogeneous for us, I think it's quite good. And at 60%, we have a fiber which is, it looks like it's like a grape of nanoparticles, which are just generating in that case. So this is one of the first tests we have been doing. And it's quite interesting because we have this it's quite small frame. We use a small frame made of Teflon, like this, and we put the membrane in between, and we just use bolts and sticks made of nylon, and we have a frame of a membrane, and we put it again. Show you at the same time. You're just using a small tube. Doesn't need to be very big. Like that, doesn't need to be very, very big. And we use this this kind of a small standing membrane reactor to test very simple systems. In that case, we use methylene blue, which is very standard dye to test the degradation, the photocatalytic degradation of a material. And we have very nice kinetic curve. You always try to adsorb first the dye, and after you turn on the light, and you have some degradation. It's interesting to see that we compared thin and thick membranes. And it's quite interesting to see there is really a small difference between them, which means that you don't need much material to have a good photocatalytic activity on the membrane. So you can, for example, imagine a sandwich structure where you have a cheap material on the membrane and an expensive-ish photocatalytic layer on the top. The loading is a bit different. The more titanium you put, the more photocatalytic activity you have, of course. We also use quite an old system we had here in-house, made of metal, and it's more or less the same size that we used for the other one. It was a system that we used for ceramic membranes. So you see the gap here is quite big, but we can adapt the system. And this is working very well also. We use small concentration of methylene blue, and when there is no photocatalyst, there is nearly no degradation. But as soon as you put a photocatalyst and some light, you see within 2 or 3 hours, you can completely degrade a suspension of a solution of methylene blue. That was okay, but then we decided to go maybe to take this step up further. So we tried to we made some 3D conception of new photoreactors and modelization. And we were a bit constricted by the machining systems that we had. We made, for example, this photoreactor, which was transparent. Could see, okay, we can see through. It can be kind of useful, but where you are quickly restricted by what you can machine, the corners, the tubings, and everything. So again, it's working very well. You use a pump to inject the methylene blue into the reactor. It's a cross-flow reactor, so you have a reaction at the surface of the membrane, but it's also going through the membranes, and then you cycle this and you degrade your water. Then we went a notch a bit up and we use 3D printing, and this is also probably a game-changing for the design of reactors. It's flexible in design. You can technically do whatever you want, whatever shape you want. For example, we curved it, then we use less material, so you can save money on your reactors. Very fast design. I remember when we started to doing this metallic reactor, this can take weeks, months before you can use it. Now, between the moment we designed and we received this reactor, it can take 2 weeks. If you have a 3D printer in-house, it can take a few days. It's quite strong, actually, and lightweight, of course. We used polyamide, I think, made by selective laser sintering. You minimize the waste, and it's very cost effective. It's very, I think it's about, these pieces cost around 50 euros, I think. It's within the same size of what I showed you before. So this is the photocatalytic results of our first test with these membranes. This is a very effective way of seeing how much particles you have in your membranes. It's thermogravimetric analysis. So you basically put your membrane in a small weight in an oven, and you're heating the oven. So the membrane is going to decompose slowly. So you're first going to lose the water, you dehydrate your membrane, and then it's burning. So you have a dip, and you're burning all your membranes in the process. So the blue light, the blue curve is the pure pan, and the red one is with 60% of particles. So the blue one is going to be completely degraded after 600 or 700 degrees, and the red one is going to be partially degraded because you still have the inorganic part in your membranes. And here the difference between the blue and the red, it's about 60%. So we know that when we say it's a 60% content titanium oxide membrane, it is actually 60%. So for the photocatalytic test, we use methylene blue also, and we really observed more titanium oxide you add into your membrane, the more photocatalytic activity. It sounds logical like that, but we had to prove that. Above 60% of loading, it was very difficult to electrospin the membrane. So there is a kind of limit where the electrospinability is not really feasible also. I mentioned before that titanium oxide is one of the only commercial photocatalysts you can find, but there is different producer of it, and we test them all. It's discussable also, but maybe we don't have time today to discuss that. What is important to remember is that UV light is much more efficient for this kind for titanium oxide. You see the difference between purely UV artificial light and solar light here. This is something which we try to develop much more recently. It's the utilization of both sides of the membrane. And again, this is something very logic for us, but when you have a photocatalytic membrane, usually you have light on only one side of the membrane, which basically means you lose 50% of the area of the membrane. So recently we proved that by using a light on both sides of the membranes, you have really significant enhancement in the photocatalytic activity. Concerning the another way, another application of photocatalysis is CO2 conversion. Unfortunately, I thought I would be able to show you a bit more what we are doing here, but we are a bit constricted by the confidentiality in the running project. So I'm going to go really on the surface here. We use the Electrospun membrane, of course, but we use titanium oxide coupled with copper oxide, because CO2 is quite a difficult reaction to fulfill. So we have to really modify the photocatalyst we are using. And we use a similar system. You pump a liquid, and the liquid contains potassium carbonates, which is going to be saturated with CO2. And then you pump this into the reactor. You have your photocatalytic reactor, which is very similar to what I show you this one. We use the 3D printed reactor, and you can produce methanol with time. So this is working. There is a lot of other things which is really interesting. I hope I will have the opportunity to show you this in the future. I would like just to acknowledge this Metamorph project. We have a lot of students. We are working a lot with Czech Republic, University of Prague, University of Jan Evangelista Pyrkne. Thank you for your attention, and I hope you have a few questions for me now. Thank you.
For a very interesting presentation. A lot of different directions of your research of purification. Very interesting approaches, not only like making nanofibers, but also like post-treatment, which is, I think, very valuable for the whole audience. So let's continue with the questions. I can see here the first one. So how does the morphology of electrospun membranes affect their photocatalytic performance?
Yeah, that's a very legit question. It's very interesting. But the intrinsic properties of the nanofibers is very interesting because it's 95% of open porosity. So it has an extremely high importance between a flat membrane, a purely flat membrane, and an electrospun membrane. It's a big difference photocatalytically. After I didn't really show it, but we had problems sometimes because the humidity, you knew more than anybody else probably in Elmarco know that the humidity is a huge problem when we made membranes. And when the humidity is not right, you can have a lot of splashes and you can have a bit less of nanofibers. So we had a lot of problems with humidity and to have reproducibility with the membrane.
Yeah, I think you just encourage everybody to use a Q&A session for the questions, right? If you have. I have one question, if I may.
Sure.
So this is a little bit more practical because you were comparing some existing membranes already. You mentioned Evonik and others. So how is the nanofiber membranes compared to those already, commercialized in terms of, let's say, capacity or performance? If you have that comparison, if you can briefly comment on that.
It's not the membrane which is commercial; it's the nanopowders.
Okay.
The P25 is the most famous and it's the most active of all of these ones. But again, I show the results, but we had a few problems of reproducibility with the membranes. So it's very strange. For example, PC500 is very known to be a good powder also, and it's one of the worst in our situation. So.
Okay, so sorry, then I was confused. But then, okay, my other question is also related to practice. So if I'm going back to the membrane, actually, that you've developed, the nanofiber ones. So what did you try, like reusing the membrane, or what is let's say, the capacity of the membrane in time? You show us some like graph, okay, but in a long term of using, let's say, or what is the liquid flow, let's say, through the membrane, or how you can determine the let's say the
Flux.
the flux or the lead time of the membrane.
Yeah, that's also a good question. We have been doing reproducibility test, for example.
Mm-hmm.
Use the membrane for a few hours, then you clean the water that you're using, and you're using another one, and you're making cycles like that. And I think after 5 or 6 cycles, we lost about 5 or 10% of efficiency.
Mm-hmm. Mm-hmm.
I suppose that if you think about an application, you will have to change the membrane also after a few cycles. I don't think you can really use the membranes eternally or for many years. So there is a bit of loss of activity with time, but up to now, what we saw is that it's not really critical.
Yeah. Mm-hmm. Yep. Interesting. So maybe we can go back to public
sure.
questions.
So one of the question is just, I think it's just to let's say highlight how you made the solution, the spinning solution. So question is related, is it let's call it one pot electrospinning or not, meaning that the fibers on the left hand side of this slide you're showing to us, very well decorated, very uniformly decorated with the nanoparticles. So this decoration comes from electrospinning solution directly.
Yes, yeah, and that's really why we work a lot on mixing the particles with the polymer at the beginning. Yeah. And that's why we went a bit away from these pure oxide membranes. Mm-hmm. This is very useful. It can be used we use it for a lot of other applications, batteries or this kind of stuff. It's super useful.
Yeah. Another question is related, like more practical, about wavelength length of the light you usually use for your photocatalytic trials.
Yes, we use UV light for most of the classic tests for methylene blue. But of course, the most important application would be to use this just by using sun. Sun is free, it's intense, you have a lot. I didn't really have time to develop this, but yeah, we are working with other photocatalytic materials also, which are non-commercial. You have to modify it, and then you can absorb a lot of the visible light also. And people which are working in photocatalysis, this is really a really extremely hot topic. And
Mm-hmm.
So it was mentioned in your presentation that surely titanium oxide has 2 main crystalline structures. It's anatase and rutile. And what is your opinion, your experience? Which type of structure is more suitable, convenient, or effective for photocatalytic application?
It's definitely the anatase phase is definitely the most active under UV light. Rutile is the phase which is absorbing a bit of the visible region, but when you mix them, and that's why P25, this powder from Evonik, is quite active, is that when you have a nice ratio between anatase and rutile, it's much more efficient also. So it's a difficult question to answer, but theoretically, anatase is much more efficient under UV light.
Okay. Yep. And also based on what you showed, that the main photocatalytic process takes place on the surface of the membrane, surely partially. Some in some pores of nanoparticles, but anyway, you have to activate these nanoparticles and photocatalytic process on the surface using UV. So there are, let's say, 2 questions then. One question is, what's about absorption of the material? What is its role? in the efficiency of the photocatalytic process? And the second part of the question is related to if the process is mainly surface one, it means that you don't need to really produce a very thick membrane.
Yes. Yes, for the most of application, of course, you want to save the most expensive layer, which is going to be the photocatalytic layer. I mentioned this sandwich type, I think, which is very important. We are also electrospinning directly on other substrate, on other type of membrane. If you have, for example, a glass fiber membranes, you can directly electrospin a layer on it, or other type of substrate. So it's very interesting, the experiment we did at the beginning when I show you the thickness. It was very interesting. We need to extend the amount of work we need to work with that, just to know if we can electrospin only 5 minutes instead of 2 hours. You can really imagine the amount of money you can save if you want to produce this kind of membrane. So it's very interesting. For the absorption, you mentioned the absorption. I didn't really understand.
Yeah. The one of the questions from QA section was related to the absorption. What is the role of the absorption of this material and its influence to photocatalytic oxidation process?
The absorption of light or absorption?
Absorption of the liquid.
Okay, absorption of the pollutants or what you want to treat. Yeah, this is extremely important, and this is where I think the choice of the polymer could have a quite big influence. The reaction takes place on the titanium oxide or on the photocatalytic particles, but if you can absorb a lot of pollutants already on the membrane, then it could be like a beneficial activity also. The absorption of pollutants on the photocatalyst itself, it's a whole branch of the science. Absorption of oxide, absorption of co-catalyst. It's really important. Yes, I completely.
And one of the questions related if any part of your presentation and your work is published somewhere as an articles.
Yeah, there is this is published, just published recently. The use of both sides of the membrane. The concept is really interesting also because on one side you could have sunlight when it's available, but when there is no sun, actually there is no reaction. So the idea would be to use like a cheap LED light on the backside, so you can have a kind of a 24 hours reaction and degradation. I can be contacted very easily also if anybody wants to discuss that or need more information.
Yeah, for example, can you imagine to really scale it up? I mean, this, because I consider that as a prototype, let's say, of the membrane. You're working in a sort of small scale. But my question is more related maybe to commercialization already, like scaling up this membrane. So what steps need to be taken in order to do that?
Yes, that's
tough question.
I wouldn't have a right answer for you. We are still trying to build some project to scale up this kind of application. I'm right out of my head right now. I'm thinking about production of hydrogen. There is an EU call which is with a deadline very soon, and we are trying really to upscale this kind of membrane to A4 size at least for that. After it's a transfer of technology, which could be feasible, of course. From the electrospinning side, of course, it's you, Elmarco. You could also upscale this kind of membranes, but it's more an acceptation of the market.
Exactly. Yeah.
To penetrate a market which is as big as water cleaning, CO2 conversion with a technology which is difficult to be accepted also sometimes. It's not easy. You will always find a university institute to collaborate, but companies, it's a bit more difficult.
I see. Thank you.
Another related question to electrospinning process itself. So you showed that you were able to electrospin pure polyacrylonitrile, and then with a loading of 10% up to 60% of nanoparticles. What's about this scaling up process? How difficult it is to electrospun solution with such high concentration of TO2 nanoparticles? It sounds like 60% of loading. It means that you are electrospinning more like nanoparticles than polymer. Actually, could be said like this. So what is let's say the difference in throughput and process in general when you go to so high loading of nanoparticles?
Yeah. That's why we are investigating. I'm coming back again to the sandwich structure, but if we could imagine just using the particle solution at the end of the electrospinning and just having a thin layer on the top. This is something we are still working on right now. And it's difficult to answer your question. But it's working at a small scale. I'm pretty sure this is working at a much higher production scale.
So you don't see very big issues when you work with the 10% loading of TO2 compared to 60% loading of TO2?
No, we were quite
NS lab.
Yeah, we were quite surprised by the easiness of electrospinning solutions with high loading like that.
And what's about other electrospinning setups? Have you ever had a chance to compare it to NS lab, like needle electrospinning? Is it still possible to work with such solution using other setups?
We did not actually, because we were very happy with what we have. But in the project we have with our Czech partners, I think it's in one of the tasks. So we are going to compare it. I can mention also that we developed these membranes based on polyacrylonitrile, and I really want to emphasize again that this could also be a big change if we use other commercially oriented polymers. Because it works very well with PAN and DMF, but you have to start over from scratch if you are using another polymer and another solvent. So it's difficult to say how far we can go for the exploitation of that.
Okay, so maybe one of the last question. Did you plan or did you have a chance to evaluate effect of fiber size, fiber diameters onto photocatalyst efficiency? Because part of particles could be encapsulated by polymer, so it could be, let's say, inside the nanofibers.
Yeah,
do you have any ideas about this?
Definitely, you definitely have a lot of nanoparticles inside the fibers, and there is a growth of the nanofibers with the increase of the loading. You are going from a few hundred nanometers to close to a micron when you have 60% of titanium oxide, for example. This might have a really small detrimental effect. I suppose when you have bigger fibers, you also have a bit less of a porosity, but I don't think it's critical. The most important is as you have as much possible as nanoparticles on the surface of the nanofibers. This is really the critical step.
Perfect.
And as green chemistry and environmental issues is a big topic. So one of the question is, do you evaluate, let's say, potential flushing of nanoparticles from the material anyhow? Do you have any ideas how it could be measured, or do you observe a flushing of release of particles?
It's part of the we consider this in the project also. We haven't been doing it, but we have a group in Sintef which is dealing with that.
Yep.
This is a really good question also from a point of view of the acceptability of the technology for the public. I can actually see the question, and I didn't see that.
So
yeah, I don't know if there are any more.
There is for the 3D printing reactor. There is a really interesting question: how did you overcome the porosity of the 3D printing material and the dye absorption? Actually, you can't. This is maybe one of the drawback of using plastic reactor. So once you are using a polyamide reactor like that for methylene blue, it's difficult to come back after. It's absorbing a bit, and we take into account the absorption on the plastic.
So, as it is always, we are running out of time earlier than we can cover all questions, because majority of questions are very, very interesting, very right to the point. So we can collect them and answer them later.
Sure, yes.
In written form. I want to thank you, Mathieu, for a very interesting presentation. One more time, I want to thank you, the whole audience, for your attention, for your question. Very, very interesting webinar again.
Yep. And I must say, actually, this very last one in this period, but don't be sad, because we are already thinking of organizing the other series probably end of this year. So everybody will be informed in time. So stay with us.
Yeah. So thank you one more time. Have a good rest of the day.
Yes.
Bye bye.
Good Easter.
Thank you too.
Bye bye.